Hi, my name is Shichen Lu, and I'll be presenting CNNs on surfaces using rotation-equivariant features. The general motivation is that we want to be able to do typical computer vision tasks, but for surfaces or manifolds. However, this is hard due to the irregularity and non-Euclidean nature of these surfaces. Several approaches have been tried. Spectral methods and GNNs both interpret the surface as a graph, and then use special graph-based feature extractors to perform common computer vision tasks. However, these are targeted more towards meshes and graphs than surfaces, and are less generalizable than the proposed method. The idea of point clouds is to sample points on the surface and then use something like PointNet to extract features from the surface. However, these point clouds cannot capture the full nature of the surface and thus loses expressiveness. Finally, we have the idea of symmetric spaces, which uses specialized approaches for symmetric surfaces. However, as noted, these are limited to symmetric surfaces, such as spheres. The approach used by this paper is what's called a charting-based method. The main idea behind this method is to use a 2D kernel to do convolutions on the surface. To do this, we first learn the kernel, then place it on a tangent plane at the point we want to do the convolution. We orient the kernel based on the basis vectors of the tangent plane, and then map it onto the surface. The mapped points from the surface to the 2D convolution define the points at which we do the convolution operation. Finally, this is repeated for every point of interest. The problem behind directly applying the charting-based method is that of rotational ambiguity. That is, we do not know how to orient the 2D kernel onto the tangent surface because surfaces do not have a predefined coordinate system. And this is the main problem that the paper tries to solve. There have been several previous approaches that deal with this rotational ambiguity problem. One idea is to define a coordinate system at each point on the surface based on a certain metric. However, this cannot guarantee consistency of the coordinate system, i.e. smoothness, in all local neighborhoods, such as at umbilic points. Another idea is to sample multiple rotations and compute convolutions for each rotation. However, this is very naturally computationally expensive, and due to the infinite amount of rotations, you cannot possibly sample in each direction, and so you have to use discretization or interpolation as a compromise. So what this paper introduces is a generalizable, circular harmonics-based convolution filter for meshes that is rotation equivariant. Using this filter, they are able to solve the rotation ambiguity problem, and they formulate this into an overall network called harmonic surface networks, which combines the above with custom pooling and nonlinearity operations to learn classification and segmentation on meshes. Using this harmonic surface network, they're able to achieve state-of-the-art / competitive performance across multiple tasks. This paper uses a couple of interesting ideas to construct their network. First is the idea of vector features, in which features are represented as a vector on the 2D plane rather than a simple number. The way they are parameterized here is using the radius r and the angle theta. Next is the idea of different types of rotational properties for convolutions. They define two different streams within their network. One, which is the rotation invariant stream, has convolutions in which rotating the input does not affect the output. The second, which is the rotation equivariant streams, has convolutions in which rotating the input, which we can imagine as a vector feature, also rotates the output, which is also a vector feature, in the same way. For the rotation equivariant stream, they base their idea off of harmonic networks, which is a rotation equivariant network used for computer vision tasks. The basic idea here is to use circular harmonics to construct the convolution filter. You can see the main function behind the convolution in the middle of the screen. Here, big R represents the learned radial profile, beta is the learned offset, and m is the rotation order. Using this, as we will see in the next slide, allows us to conserve rotation between the convolution. Here we see a toy example of two different types of convolution kernels operating on vector features. On the left, we have the rotation invariant version, and on the right, we have the rotation equivariant version based off the harmonic networks previously mentioned. In this example, we can see that the black vectors are the output of the kernel, and the location of the black vectors represents the vector feature input. When these convolution kernels are applied to a surface, we can see that in the rotation invariant case, the output feature vector, which is represented in yellow, is always aligned with the x-axis of the tangent plane, regardless of the rotation of the tangent plane respective to the surface. On the other hand, in the rotation equivariant case, the output feature vector is aligned with the same direction respective to the surface and irrespective of the orientation of the tangent plane. Here we see another example with the same convolution kernels operating on an input which is half low activation and half high activation. In the rotation invariant case, we can see that the output vector feature is a smooth version of the input. However, in the rotation equivariant case, we can see that the output vector feature not only identifies the position of the edge on the input, but also the directionality of the edge. Intuitively, we can see that the two different convolution kernels can capture two different types of information. In harmonic networks, this is formulated by having two different streams, the m equals 0 stream, which corresponds to rotation invariant, and the m equals 1 stream, which corresponds to rotation equivariant. Here they have convolutions both through the streams and between the streams, and use this to capture the two layers of information. Going back to a couple of ideas used by this paper, we have the idea of parallel transport. Because manifolds are non-Euclidean spaces, we can't compare vectors from two different points because they are defined on two different tangent planes. Instead, what we can do is transport one vector from one point to another and then compare them at the same point and on the same tangent plane. In this paper, they use the vector heap method, which solves the parallel transport for all vectors to all other points simultaneously. Finally, we have the idea of exponential mapping. This is a map that defines a relation between the tangent plane at a certain point on the surface onto a point on the actual surface. In this paper, it is used to apply the 2D convolution kernels onto the surface by mapping to the surface point and then applying to the convolution. Now let's move on to the network proposed by the paper. The overall goal is to take in a triangle mesh of an object and output the shape classification, segmentation, and correspondence results. To do this, they formulate all the previously mentioned ideas into an overall convolution kernel. In this example here, we can see that we're trying to calculate the feature at layer L+1 and point I. To do this, we first find all the neighboring features based on a geodesic ball. For each neighboring feature, we parallel transport it into the same tangent plane as I so we can compare the feature vectors. Finally, we apply the circular harmonic function to do the convolution. Here we can see that the combination of parallel transport plus circular harmonics is able to eliminate the rotational ambiguity and produce a rotational equivariant feature. Additionally, they also define a couple of custom nonlinearities and pooling operations for their network. For nonlinearities, they use ReLU. However, it is applied to the radial component of the feature only with an added bias because radius is always positive. Pooling works in the same way as normal pooling. However, vectors are first parallel transported to the same tangent plane before comparison. The overall network architecture is very similar to a UResNet architecture. Here, the input is the XYZ of each point in the triangle mesh, and the output, in this example, is a classification result over all the n classes of the dataset. Note here that they have defined the ResNet block, Rn and shown in green, as a combination of the two streams mentioned earlier in the harmonic networks. For results, let's first start with shape classification. Here we can see that HSN outperforms all compare techniques by a significant margin. Additionally, they only use the first half of the network and only train for a quarter of the time. Some reasons for why this might happen are firstly that the dataset that they are training on has a very low amount of training samples and may favor methods that use less parameters. Additionally, the dataset has very low quality meshes, which may be unfavorable for other methods that rely on principal curvature. For the shape segmentation results, we can see that HSN performs competitively but falls behind Mesh CNN. One reason may be that they only sample 1,024 points from each mesh to reduce computational time, and is potentially able to achieve higher accuracy with more samples. Additionally, the authors also visualized feature outputs for one feature stream in the second last layer, as shown on the right. Here we can see that this layer is able to learn rotationally aligned features that sort of correspond to the heads, arms, and legs of a human. For the correspondence results, HSN again outperforms all comparisons, and this is particularly evident in the datasets with irregular connectivity between shapes, in which HSN is able to demonstrate its robustness to connectivity and differences between meshes. Overall, we can see that HSN performs fairly well. Mesh CNN sometimes does better, but deals explicitly with meshes, unlike HSN, which can be applied to both surfaces and point clouds. Additionally, HSN performs significantly better than MDGCNN and GCNN, which follow a similar charting method but uses much more compute than HSN. Here the authors did an ablation study on the effectiveness of using parallel transport and the rotation-equivariant kernels. We can see in the results that dropping either one of these techniques significantly decreases the accuracy of the network. However, there are a couple limitations. Firstly, this requires the vector heap method for several calculations. This method performs poorly if the mesh is low quality or has too few elements. Secondly, the results are not the best. It's outperformed by mesh CNN in segmentation, and another paper has shown HSM performing just about average in correspondence tasks. Finally, there's a high computational processing requirement. The vector heap method requires many pre-computed operations and can struggle for complex tasks or meshes. And even in the results section, they need to downsample the number of vertices for a reasonable amount of training time. Overall, we have seen harmonic surface networks for surface classification, segmentation, and correspondence. They use a rotation-independent approach based on rotation-equivariant kernels and parallel transport to solve the rotation ambiguity problem, and are able to achieve state-of-the-art / competitive performance across multiple tasks.